Hi, in this video I will be talking about my junior design project for Oregon State University's Junior Design 2 class. This is a digital oscilloscope. I'll be talking about the specifications of the oscilloscope and then sort of the design process that myself and my team went through. My other team member was Brennan Ventura. We worked together on this project. So the main features of this oscilloscope include that it has two channels. It is portable. You can see, it's a small form factor. It has a battery pack built in, so I can turn it on. No external power is required. It uses normal oscilloscope probes, so it uses BNC connectors here to connect and disconnect. It also has a user interface that is easily adjustable using a graphical user interface on the oscope itself. And finally, it has good fidelity, so it has a sampling rate of greater than 1 megahertz. During the junior design class, you are given a set of engineering requirements for your project, depending on what project you choose. During the design process for this project, our first step was to look at our engineering requirements. The engineering requirements we had to meet initially were that the oscilloscope had to use robust connections and have two channels. It was also a requirement that it had to sample at a rate of at least 1 megahertz, so be able to accurately recreate signals that are at least 500 kilohertz. The final predetermined requirement was that the oscilloscope have a responsive and intuitive user interface. And then Brennan and I also added another requirement, which is that the oscilloscope would be battery powered and portable. After we figured out our engineering requirements, the next phase was to sort of just start piecing all the ideas together that we needed to move on to the next. So ideation, figuring out, okay, what are we going to do? What are some of the possible methods we could use to implement an oscope? Like, what microcontroller can we use? Do we want to use a built-in screen? Do we want to use an external monitor? How are we going to do the sampling? Are we going to use a microcontroller with an analog to digital converter built in, or are we going to outsource the analog to digital conversions to a separate microcontroller? All these were sort of ideas and thoughts and decisions we had to sort of think about what consequences would those have depending on what we chose. That was the second step of the design process. Once we'd had some time to think about how we might implement the project, we started doing things like picking parts. We researched several different microcontrollers we could use. We had decided that we would prefer to use an analog to digital converter that was already built into a microcontroller. So we were looking at microcontrollers that were fast so that they might be able to sample at 1 megahertz. We were doing research on if people had previously been able to sample that quickly with a given microcontroller. And then we were also doing research on other options in case sampling with the built-in ADC of a microcontroller was not going to work. Once we had determined what microcontroller we were going to use, it was pretty easy to pick the rest of the components surrounding it. So we picked a screen that was small and portable. We picked rotary encoders for the user input, push buttons as well, and then BNC connectors and a battery box. And that was essentially all the parts picking we had to do. After we had sort of figured out what approach we were going to take to make the oscilloscope and what parts we were going to use, the next step was to actually start designing it. So figuring out, exactly how are we going to take these analog signals in? How is the circuit going to process these analog signals so that it doesn't harm the microcontroller and so we have a better input range? And then how's the microcontroller going to sample those? How's it going to store that data? How's it going to display that data on the screen and manipulate it based on the user's settings? And of course, how is it all going to be powered? How will all the signals be routed around to each other? What sort of dials and interfaces will we need for the user to physically interact with? The knobs for rotary encoders, the push buttons, how many of each would we need? Where should they be placed? What functions would each perform? We had to think about all that and make some of those design decisions. And then from that sort of groundwork of here are the basic requirements sort of fleshed out into something a little bit more concrete, we started actually designing specific blocks. Brennan worked on the user input block, designing the hardware for user input, designing the software for user input. Brennan also worked on making sure everything was powered through a portable battery pack, so determining the current draw of all the components, determining how much voltage each component needed, determining how we could power that and how long we would be able to power it, as one of our requirements was not only that it was portable, but that it could be run for at least 6 hours off of a battery pack. Just a quick editor's note here to interject that I forgot to mention Brennan also designed the circuit board for the oscilloscope, a pretty significant block, important obviously to connect everything together, so wanted to make sure that was in there. Some of the blocks I worked on included the sampling block, so determining how to get from an analog signal at the end of this probe into the BNC connector, into the circuit board, how it would be filtered and scaled before going into the microcontroller. And then once inside the microcontroller and software, figuring out how to sample that at the right rate, how to store those samples, and then how to do conversions on those samples in order to display them in the user interface. I also worked on the user interface block, and then finally towards the end of the project, I worked on integrating all the blocks from both my own work and Brennan's work all together into a coherent enclosure like this one. Finally, once everything was integrated together, the last step of this project was to do the final verification. So go back to those original engineering requirements and write testing plans to make sure we could meet each one of them, to figure out if we could meet each one of them, and then execute those tests to make sure our oscilloscope was actually meeting all those engineering requirements, to make sure it was sampling at a rate of 1 megahertz, to make sure it was portable and the batteries could last for at least 6 hours, to make sure that the user interface was responsive and not laggy, to make sure that, it had 2 channels and it was easy to connect and disconnect to. That part was pretty easy, obviously. And then just making sure everything worked. So overall, I think this was a pretty fun project. I feel like I learned more than I expected to, honestly. I went into this thinking like, oh, building an oscilloscope shouldn't be that difficult. And well, really, in theory, it's a pretty simple theory of operation. You have an analog signal, you put it through an analog to digital converter, you sample it at a specific rate, and then you use those samples to draw pixels on a screen. There's a whole lot more behind the scenes that goes into that, like figuring out how to trigger to make sure your sampling happens at a specific interval based on the shape of the waveform, making sure that the waveform is scaled appropriately to the screen, making sure you can change the sampling rate so that you can accurately recreate signals at a wide range of frequencies from like 1 megahertz all the way down to like 10 hertz. So there's a lot more going on behind the scenes, and I think I really learned a lot about that, and also just a lot about how analog to digital converters, especially analog to digital converters that are built into microcontrollers, work, and some of the limitations of those and the ways to get around those. Overall, I think it was a good project. Got some experience working with a team member as well. So yeah, definitely recommend junior design to any ECE majors. I mean, you'll probably have to take it anyway, but it's a good class. I think you'll learn a lot.